I am Miora Mandea, and it's my pleasure not to be the convener, but to chair this very first part of the session. And we have, for this part, 3 invited speakers. And the very first one is Volker Liebing, the director of ESA Observation in ESA. And he's going to tell us about ESA Earth Observation in support of geosciences. Volker, the floor is yours.
Yeah, thank you, and good afternoon. I try to wake up after the meal and tell you a little bit about what we are going to do in our ESA program. So we are living in exciting times, also for Earth observation, for geosciences. But it's also times with big challenges. So we see a lot of these challenges influence what we do, which is on the one hand a very good thing. On the other hand, as I said, we are also under certain pressure to deliver. So the most important issues I feel which we are at the moment facing, you see a little bit on this graphic. I would like to start with population growth. So we will have 2 billion people more before 2050. This is combined, of course, with the necessity to almost double the food supply, because middle class is developing in China and India, starting to eat meat. So we need about 10 times more cereal for that. We need the water for that. 85% of the fresh water consumption on this planet goes in food production. So FAO has estimated something between 85 and 115% we need to increase by 2050, which is only 35 years from now. It's not. It's in our lifetimes, at least in the lifetimes of most of the people here in this room. Then climate change, of course. This is a bit more long-term, but nevertheless, it's occupying us quite some time. And in our lifetime, we will see already impact of climate change, especially when you live, let's say, close to the Arctic. There, it's most evident when in the mid of this century, another 30 years, the summer ice will more or less have disappeared. We have just seen a wonderful animation from Mike Freilich at the Hyperwall of NASA at the lunch break, where you could see this. But we have also other changes which come more from the technology side and which change rapidly Earth observation. And this is the IT development. We are entering the times of so-called big data, and this has also meaning for what we are doing, and I will come back to that. Last year was a very important year for, let's say, giving us objectives and goals for the years to come on this planet. And I think a landmark was the Paris COP21 meeting for climate change, because now for the first time 190 plus nations have agreed to a target, to an objective, which is a +2 degree with an effort to reach 1.5. The key to that was that one has gone to intended national determined contributions. That means everybody could determine himself more or less what he would be willing to contribute. But we also know that if we sum this up, it leads to something like +2.7 degrees, depending on what is the real forecast, and not to 1.5 degree, which is at least the hope of the island nations close to the equator that we would reach. So there is something to do. And there is also a lot of issues in the COP21 agreement, like reporting every 5 years, stock taking, mitigation measures, where Earth observation will be a tool. And the second big, I think, objective setting last year was UN Sustainable Development Goals, which have many, many aspects, and many of these can also use, at least as indicators, our Earth observation data. And what I mentioned before, food supply, water supply, energy supply is all in it. And if we look into Europe these days, we have a big immigration problem because migration, also based on, by the way, climate change, partly because some years ago we have seen in Syria a big drought, which has caused some million farm workers to move into the cities, which increased the pressure of the conflict we see at the moment. IT, I mentioned already, I live in Rome, and I show you here two photos. When the Pope was elected, the second but last, it was 2005, St. Peter's Square, when they announced this, and then 2013, when they announced it. So evidently, something has changed in these 8 years, and we have also in Earth observation seen that we are in the middle of a second revolution. I say we had already once when they invented high-speed networks, when we started to use robot archives, when we had the internet, and when we suddenly could process image data on workstations. So these were all, let's say, for me, the first IT revolution, which gave an enormous push to Earth observation, because I remember well in the 80s the discussion about data graves, because we produced much more data than we could process. And we had hundreds of meter-long shelves with old magnetic tapes, 1600 BPI, if I remember, etc. So some of you might remember this time. And this is changing completely. We are entering a time of petabyte. And this also means that we cannot download all every more in the future. We still do it, but this will change. We have to bring the users to the data. So we will see different, let's say, approaches to that. And in our program in ESA, we prepare for that. There is also new issues, how we collect data. So they are also a bit connected to what is called Science 2.0. I will come back to that, where one issue is absolutely clear. It can only work if you have open and free data. And I think here there's a consensus, I'm sure in this room, for sure also between NASA, ESA, and many other space agencies, that this is an extremely important issue to be able to deal with this new IT world. Now, here's an indication of what is the increase in data which we expect in ESA. So you see, oops. So you see here the time, the green is the Envisat era, and the blue is when we started, the violet, let's say, with the Sentinels, and we are more or less here. And now we have almost an exponential growth in terms of data with any of the new Copernicus missions up in the orbit. So now let me come to the program of the European Space Agency, which tries to give some answers, some help, some support for the challenges to come, and also using, let's say, the opportunities from this, what I have described to you. And let me start with what we call our Earth Explorers, which is scientific missions looking into the processes, because nowadays science needs both understanding the processes, but then also make long-term monitoring. So we need both components. And this is the component looking into understanding the processes. And I like to start with GOCHE, not only because EGU is also a bit a synonym for the classical, in inverted commas, geosciences. I'm myself a geophysicist, so my heart is close to gravity. So other geopotential fields, of course. So GOCHE is already back to Earth, but it was one of the most innovative missions. And what I wanted to point out here is that there is still a complete generation of scientists working on the data with key publications. I have put one here on the screen, which I regard as a very important one of 2016. And a lot of data are still not processed, let's say, in the sense that there's a lot of science still in the data, and it is used. Even a new science discipline, which is the re-entry part, because this satellite has flown further down before it was destroyed and has delivered further down data than any other satellite before. And I think it's a treasure box of data. I would also like to mention that two of our missions have data sets which are academic. These are the geopotential field missions, the gravity mission and the magnetic field mission, which you see here, which is in fact 3 satellites in our swarm, where you find products nowadays in your mobile phones. Because when you want to transform GPS altitudes into altitudes above sea level, you need a GeoEd, and the latest GeoEd, which has been given out, is strongly, at least, is strongly also dominated by GOCHE data for many of the components, especially the higher ones. And For swarm, it's similar. The geomagnetic reference field has profited a lot from the 3 satellites, making a very thorough investigation of our dynamic but also static magnetic field, which protects us from the solar wind. Also an exciting mission, I have to say. Especially also because we have, from our colleagues in space science, we have still the cluster satellites in orbit, which are on the outer side of the magnetosphere, while the swarm missions, the swarm satellites fly at the lower part of the magnetosphere. Then ESA's Soil Moisture and Ocean Salinity mission gives global data sets for the 2 parameters I mentioned, soil moisture and ocean salinity. Since February 2010, the satellite is very healthy, so we extended it until 2017, and if everything goes on, I don't see a reason why it should not live longer. I think both are very important data sets which are used in many applications meanwhile. This, for me, is one of the most important missions we have flown, because Cryosat gives us really precise information about the ice thickness, especially also the sea ice thickness, also of the other, but also of sea ice. And I mentioned before that in our lifespan, the most visible climate change related change on this planet is probably the disappearance of the summer sea ice in the Arctic, which opens new sea passages. To make a simple example, between Europe and Asia, or also between the America and Asia, it's much shorter. And this will be used for sure. At the same time, it's access to resources. I personally hope that the hydrocarbons stay where they are. I hope it's too expensive to exploit them, because when we look at the COP21 targets and we see that our contributions lead us still to 2.7 degree plus, which means then at the poles about 6 times as much, then you can imagine what it would mean. This is one of the results. Some years we have already 15 meanwhile. You see, as I said, also that the extent we measure since some decades, and it's very good, but the ice thickness, we had only 2 missions to my knowledge which have measured it in this precision. A NASA mission and now Cryosat, and I hope another mission will follow on again, so that this flow of information is not interrupted, because the volume of the ice is important, and especially also the multi-year ice, which you see in the thicker parts of the ice. It's also wind dependent, by the way, because sometimes the ice is moving below each other, and then you have a doubling of the ice sheet. We have more missions in the making. By the way, at the moment in ESA's order book, so to speak, we have 31 satellites to deliver, which are fully financed, which is in history the first time that we have reached that. 2 of them are these 2 missions, Aeolus, looking into wind vectors. For the first time, we try to measure directly wind vectors with a laser system. Very complicated, I have to say. Lasers in vacuum is something in itself, a research topic. But we hope end of next year, beginning of the year after, we hope to launch it finally. We have now the flight models of the instruments delivered. And we have the EarthCare mission, which looks into aerosols, radiation, cloud, and the interrelation. This is still an area of research where we don't understand everything in our atmosphere. 2 more innovative missions have been decided last year by ESA's program board. One is the biomass mission, which will look with a P-band radar into the biomass, as the name says, so mainly also to reduce the error bars we have in the estimate of the tropical rainforest biomass. The boreal forest we know a bit better because it's in areas where you have a forest statistic, so the error bar is a bit lower. But for tropical rainforests, the error is above 40%, which is enormous, and we try to get it down at least to 20%. And for that, we want to fly a P-band radar. So we need a 12-meter diameter antenna, and we have here a cooperation for the antenna structure with NASA, so that we fly that. And then the latest decision was on FLEX, which is a mission looking into plant fluorescence from orbit. This has been demonstrated already from planes, but never from orbit. It's a tiny signal, so I learned a lot when this proposal came about photosynthesis, because it was not clear to me that when a plant gets energy from the sun and is stressed by any means, water or other stresses, then it does not use all the energy, and part of the energy it emits again as a fluorescence. And this signal, of course, contains physics, and this is what scientists are interested in. So I think this is a very exciting mission, which we are looking forward. So these were the processes, but then there's the other side, which is long-term monitoring. It was always clear, latest after the ENVISAT experience, that scientists need long-term data supply, but not only scientists, because many of the applications have become now operational. And this was the reason why the Commission and ESA have decided to go for an operational monitoring for our planet. What we have done 35 years ago, more or less for 40 years almost, for meteorology, we wanted now to also start for environment and civil security, by the way. And so there was a family of so-called Sentinel satellites developed, which is now, well, let's say 1.5 years from the completion of the first generation of the family. I have already signed the contract for the so-called C and D unit. So the first generation will consist of 4 satellites each. 2 will always be at the same time in orbit. We have 1, 2, and 3 in orbit. So the radars, the optical component, and let's say a kind of an ocean satellite with a radar altimeter, but also with ocean and land color instrument and temperature radiometers on board. And we will have an atmospheric component with a precursor mission still launching this year, and the 5P, and then instruments following on the next generation of meteorological satellites, which we develop for EUMETSAT. Just some examples of the satellites which are in orbit since 18 months, more or less. Sentinel-1A, here Greenland with the ice flow. What is also new on the Sentinels is not only that they are operational, but that they deliver also data in an unprecedented frequency. With the 2 satellites, we will have 10-meter resolution data from the whole planet available every 6 days for the radar component and every 5 days for the optical component. And this is really a step forward. And this one here is now taken by radar images because we have only 1 satellite in orbit with 12 days difference. So you have also already a very good resolution, because the swath of these missions is also extremely wide. And you see here that there are speeds of 16 meters per day, up to 16 meters per day in the ice flow. And you need, of course, also relative frequent measurements to get a bit the fine structure of these flows. Yeah? So the more frequent, the better. And in fact, in 4 days, I will fly soon to Kourou, where we launch our satellites. And on Friday, please cross your fingers, we are going to launch Sentinel-1B. And I hope everything will go well with that. So now we have a high frequency of the measurements, but we also have long-term archives. So if I take, starting with CSAT in 78, for example, here for some glaciers in Greenland, the ice edge, then you see what developments this has taken over, 4 decades almost. Here's an example of coral reefs in the Red Sea from Sentinel-2. Which delivers 10-meter optical data, which are very good in quality. Or here's an example of mapping water bodies from the same data sets. All data sets, as I said, you can download. It's all open and free. And we serve, the system was built, of course, for some 80 operational services of the European Commission. But we have, meanwhile, many tens thousands of self-registered users, mainly probably scientists. So these are first data from Sentinel-3, which is still in the commissioning phase. Just to give you an example, here's this little stripe here is the radar altimeter. You know, the new radar altimeter on board has a resolution of 300 meters, so it has improved by about a factor of 10, more or less. and it is overlaid to other radars which are already calibrated and validated, radar altimeters, sorry, like Alticar and JASON, and you see it fits relatively well even before we have finished this phase. Here's an example of the sea and land surface temperature radiometer, a very stable temperature measurement instrument, radiometer. And here you see it's from the peninsula, the Antarctic Peninsula. Here you see a crack. The crack is between 2 and 4 kilometers wide and hundreds of kilometers long. It just shows an example of the first images we have taken. This was really one of the first images from SLSTR with a storm system over Spain. So here you see Spain. So the satellite is in good shape. We need still a couple of months to calibrate and validate all the data. We are in heavy motion here, and then it will be opened for all of you. I already said that we are in a time of big data, we have, as I said, about 30,000 self-registered users, meanwhile, who have downloaded about 4 million satellite images since we have started Sentinel-1, since we switched the archives open or the data flow open, because you have access to both the historical data and the actual data, which come down within 3 hours. They are online available after acquisition, and on this address you can find where you can download them. I mentioned already the COP21, and of course we look intensively into what can we contribute beyond what we already plan. And so we are discussing with the European Commission on CO2 monitoring system, which at the end I'm sure will not be a European system, it will be an international system in cooperation. But there was a study just some days issued before the COP21, and it was, let's say, asking to set up a European component which not only measures CO2 in one point, but measures also fluxes, and at least for the biggest sources is able to distinguish between Anthropogene and natural CO2 emissions. And for that, what you need is an imaging system which measures CO2, and in combination with I name it classical CO2 measurements. ESA has worked on such a technology since for phase A and B in the CarbonSat context, and we now discuss with the Commission whether we can make until 2025, let's say, a demonstration mission, and then until 2030 an operational mission consisting of a couple of satellites with this technology. And when we have made a bit progress with the Commission, because this is the financing side, then we will, of course, start also our negotiations with our partners in different countries. The climate change initiative, climate change variables have been defined by GCOS, and we intend to continue this program. We have developed already some global data sets which are very important and have also made its way in the IPCC report. And for the next IPCC report, it will be also very interesting. You know, after COP21, IPCC also got the requirement to deliver a scenario for plus 1.5 degree, which is not existing, interesting enough. And we are also looking forward to that. I mentioned already the big data time, and in big data time also science changes. So ESA does really an effort to relate to open science to zero. We have started a lot of things. One of the basic principles is, of course, that all is open and free. So all is transparent. So all the data and also our toolboxes are open and free available. We try to use more and more big data analytics. I have shown you how the data storages will develop. So we are going in the time of many, many petabytes of data, which you cannot download for each single user anymore. So we plan exploitation platforms where you will also have processing capabilities in cloud and server farm similar installations. We have already started with example of citizen science. So crowdsourcing is something which fits naturally to Earth observation data, especially when you go to global data sets. So we have tried something with air quality where a little polarimeter was given to users who were interested. So 3,200 participants with their mobile phones made measurements on ground of aerosols and were delivering this via a software tool, and this was combined with the satellite measurements. A similar thing we did with land cover. So we got 250,000 ground truth data for land cover, and I can tell you when we hopefully go to have a global land cover map like Globe Cover, which we did with MERIS, a 300-meter resolution, but we have also the ambition to do it once with the Sentinel-2 data with 10-meter resolution. So it's 900 times the number of points. Ground truth, I'm sure, can only be made if we use this type of methods. And we have also started with massive online open courses. We made recently one for climate change, and we had 16,000 participants online. So we reach suddenly so many more people in these questions compared to what we have done. At the end, I would like to give you a short outlook on what we are going to do on the ministerial. ESA is financed by ministerials, its programs are financed. So in December we have the next with our 22 member states, and what we will present mainly is our Earth Observation Envelope program. This is our science and technology program with innovative missions. Flex, I showed you, a new Earth Explorer will be part of it, which we have still then to define. We plan a companion satellite to the SAO Commission, an L-band mission from Argentina, a small mission to have a tandem with a passive satellite. We plan to develop the CO2 monitoring instrument, which we need for this CO2 monitoring system. And we will work on the next generation, the definition of the next generation Copernicus, together with technology developments and studies. And also we will continue our application program and the science program I mentioned to you. At the very end, we are here on a huge conference. I would like to point to a smaller one, which nevertheless we have already received 2,800 participants. I think for remote sensing alone, it might become the biggest of the planet ever. In Prague, on the 9th to the 13th of May, the so-called Living Planet Symposium. And I hope I see some of you here back again. Thank you for your attention.
Many thanks, Volker, for your tour around the Earth. You know that at the end of the session we'll have half-an-hour discussions. However, if there is one single very urgent question for Volker, I will be happy to take it. Please.
Can you slide about the climate change initiative about essential climate variables? Solar spectral and total irradiance is not included, but it is essential climate variable. So are there plans to cover it?
Well, in fact, there are 40 essential climate variables. ESA is covering at the moment 11 or 12. Some others are covering others. And Mike gives me a sign, so I think he might make a remark on that. I transfer this to him, but it's an international effort. That means other agencies cover others. And by the way, there might come new. I was recently on a climate change conference of Chicos, and they look into even define new ones because time has evolved. And also seeing COP21, we might need new indicators.
Okay, thank you very much, Volker, again. So we move on, and the next talk will be given by Michael Freilish, and it's from NASA, looking down to the Earth. Mike.
Here, let me just get these started. Well, thank you very much. It's a real pleasure to be here talking to EGU and giving a brief overview of NASA and our partners' research Earth observation missions. So actually, let me get started right away. How do I? Yeah, okay, I got to do this. Maybe.
Need to scroll.
On this one. Okay. Thank you. So, oftentimes when I give similar overview talks like this, oftentimes inside NASA, I have to give an explanation for why is it that NASA, the US Space Agency, is looking back at the Earth instead of looking out. But luckily for you people in this group, I don't think I have to belabor the point very much. Space agencies observe the Earth basically because it's a really hard problem. Earth is a complex system that we want to understand in integrated ways, not only the individual processes themselves, but also the linkages between processes. And the problem is actually uniquely amenable to system engineering solutions. And we as space agencies are nothing if we are not excellent system engineers. I'll talk in a little bit about the fact that the ability to look at the Earth from the vantage point of space is absolutely crucial and allows us to do Earth system science as opposed to Earth science in pieces. The importance, as Volker has pointed out, is extraordinarily high. We have the opportunity through our measurements, through our research programs, through our understanding, and as Volker pointed out, through our development of actual products to deliver societal benefit, to show how the nation's investment in our science and our measurements actually helps to improve the lives of every single person. And finally, again, as Volker pointed out, no single agency, no single nation can possibly tackle this problem themselves. So cooperation is absolutely necessary, and I and we heartily endorse and have long followed Volker's call for free and open data exchange. So the vantage point of space, as I said, is revolutionary and absolutely essential. Only from satellites can we make measurements that have high spatial resolution but global coverage. Only from satellites can we make measurements frequently at each point for long periods of time with consistent processing and stable accuracy. What I show here on this chart is NASA's, not the US's, but just NASA's research satellite fleet for now and in the future. The lower half of the chart down here, where the mission names are shown in blue and green, represents all of our ongoing, on-orbit today missions and major instruments. We're at the upper portion of the chart, where the mission names are in orange and yellow, show the NASA research missions and instruments that we will be launching between now and about 2022. They are all fully funded. Some of them are going to be launching in just the next few months. So I'm not talking about things that are only going to be launching 7 years from now or so. And you can see that international cooperation is absolutely essential. More than half of our on-orbit and planned missions involve significant international collaboration through hardware contributions, let alone through integrated research teams. And in answer to the question that was asked earlier about solar irradiance, actually we are presently flying both the SOURCE mission and the TCATI mission joint with NOAA to measure solar irradiance, and we have plans to launch the radiation budget instrument as a follow-on to Ceres, as well as the TSIS-1 and TSIS-2 instruments that will be flying on the International Space Station to provide spectrally resolved solar irradiance operationally for long term into the future. So again, this is a schematic animation of our some of our research Earth observing satellites. You can see most of them are in polar orbit, but not all of them. Some of them are in an inclined orbit. We are flying instruments on the space station because it makes sense and it's actually low cost for us. And you can see that we're flying some missions in actual constellation. This is the so-called A-train that's flying right now, 5 international missions flying close to each other, making nearly simultaneous measurements from a variety of different look angles and in the atmosphere and of the Earth. And this is the International A-train as it exists right now. Parasol is out of it. But by flying multiple missions in close physical constellation, we can actually take advantage of the fact that we can align measurements that are taken at different viewing geometries necessarily so that they happen at the same time. So the virtual observatory that we have created from these constellations is actually far more capable than any individual satellite could possibly be, even if we hung lots and lots of measurements on them. And key to the A-train and key to all of this is, in fact, free and open data exchange, so that from a scientific standpoint, we can take all of the relevant measurements and analyze them together to address a particular science problem, as opposed to simply analyzing those measurements from a particular mission that might contribute to a science problem. We're not only making measurements from low Earth orbit, we're not only making measurements from geostationary orbit. Recently with NOAA, we have completed and launched the Discover spacecraft, which is mostly a space weather sentinel at the L1 point, 1.5 million kilometers from Earth, more or less on the Earth-Sun line. But there are 2 instruments on Discover, the NISTAR radiometer and the EPIC imaging radiometer, which are looking back at the Earth. From 1.5 million kilometers away, one can actually see the entire sunlit hemisphere of the Earth simultaneously, not stitching it together from a number of orbits of low Earth orbiting satellites, but rather making rapid measurements with the EPIC camera with about 8-kilometer nadir resolution over 10 spectral bands of the entire sunlit hemisphere of the Earth, more or less continuously. And of course, if you're 1.5 million kilometers away from Earth, then the moon is between you and the satellite and the Earth, and every now and then there is in fact a lunar transit. And I might point out that probably even the Romans could have predicted when those transits would take place. This is the first one that we actually observed from L1 with Discover. And what you see as far as the moon's face is concerned, that is the face of the moon that faces the sun, the one that we call the dark side of the moon. You figure that out. But we also do science from Discover, EPIC camera. I said that there were 10 spectral bands. Some of them can be combined to actually get integrated stratospheric ozone, again, more or less instantaneously over the entire sunlit hemisphere of the Earth, instead of necessarily trying to piece together the measurements as we're doing now from our low Earth orbiting instruments such as the ozone mapping and profiling suite on SUMI NPP. And you can see that thankfully the two stratospheric ozone measurements from EPIC and from low Earth orbit are thankfully quite similar. And talking about stratospheric ozone, this is an example of how from space over long periods of time, we can actually monitor critical variables to give indications not only of the science and the processes that are going on, but also of the efficacy of policy decisions. You know from the Montreal protocols that the nations got together with the objective of decreasing chlorofluorocarbons in the upper atmosphere in order to reverse the ozone depletion in the stratosphere that was happening. From our spacecraft, we have been measuring total stratospheric ozone, here expressed in terms of the size of the Antarctic ozone hole as a function of time. The model predicted that we would be just about at a maximum in terms of the extent of the ozone hole right around now. But over the next 50 years or so, the ozone hole should be filling in, stratospheric ozone should be increasing. We're in a position now where we will be making those measurements continuously and feeding back to the policymakers about the efficacy of those policy decisions. Similarly, we are now making measurements with high precision and accuracy of global atmospheric carbon dioxide in NASA with the OCO2 mission. And you well know that carbon dioxide, as Volker pointed out, is a potent greenhouse gas. It's closely connected to the temperature objectives, temperature rise objectives that COP21 and the other nations are talking about. The objective of OCO2, though, was actually to measure atmospheric carbon dioxide mixing ratios with a specific emphasis not on the anthropogenic sources, but rather to understand the processes of the large extended natural sources and sinks, like the boreal forest and the Antarctic circumpolar current. From the global measurements from OCO2, now more than a year old, it's almost 2 years old, we can actually see the evolution of carbon dioxide concentrations in the atmosphere from the end of the winter towards the spring, and as the plants green up in the northern hemisphere, photosynthesis sucks down carbon dioxide, so there's a net flux from the atmosphere to the land, and you can see that carbon dioxide mixing ratios are actually decreasing. I might also point out, since Volker mentioned the solar-induced fluorescence, that there is an experimental solar-induced fluorescence product that's being produced globally from OCO2 measurements right now. It's not optimized, the mission was not optimized for solar-induced fluorescence, but as Volker pointed out, under almost any stress, a plant which absorbs a photon either has to get rid of it through photosynthesis or heat up and die or emit through fluorescence. So it's a sensitive indicator of plant health. NASA has been flying moderate resolution land imaging satellites, Landsat, for now more than 43 years. And that actually serves as the longest spaceborne, consistently processed, continuous set of terrestrial measurements that our species has ever accomplished. We can now access that entire data set, process over significant periods of time, here over about 13 years from Matt Hansen and his group, the changes in forest cover at 30-meter resolution globally over decades. And a number of different aspects of that analysis are shown here with tree cover, forest loss, forest gain, and loss and gain together. The interesting part that I find here from this chart is down here in the southeastern United States, for instance. That is the region, perhaps in the world, of the largest forest loss and forest gain over this period of time. What exactly does that mean? Well, these are all managed forests. So on a 50-year cycle or so, the companies cut down the trees and replant the trees. And so what we're actually seeing is the result of humans managing the environment for our benefit. In a bit of the remaining time that I have, I'd like to talk about one of our real triumphs as a species. From the vantage point of space, we're now making measurements of virtually every aspect of the hydrologic cycle. The reservoirs, surface and subsurface, the fluxes between the ocean and the atmosphere, and the land and the atmosphere, and the solid water. And I'd just like to take us on a little tour through those satellite measurements to show how we can put them all together to understand the Earth as a system. We know with accuracy and precision, thanks to precision altimeter measurements that we have been making with all of our international, well, our European international partners since 1992 or thereabouts. We know that in a global mean sense, sea level is rising at a rate of 3.2 millimeters per year, plus or minus about 0.4 millimeters per year. That doesn't mean that it's rising everywhere at that rate. There are some places where sea level is actually falling over time. There's some places where since 1992, sea level has increased and then it has fallen. But in a global mean sense, sea level is increasing about 3.2 millimeters per year. We know that from the consistent multi-mission satellite altimeter data record. But the question is why? Well, there are at least three reasons that sea level could change that are of some interest to us. One of them is you take water that was on the land, say in land ice sheets and glaciers, and you melt it and you put it into the ocean, adding mass to the ocean. Another reason is that over time you can change the shape of the ocean basin. That would change the sea level. Now, that sort of time scale, the geological one that we're talking about there, that's more appropriate to graduate students finishing their theses than it is necessarily to the science at hand. And of course, there's the third reason for sea level to change, which is that the density of water in the ocean, owing to temperature changes in the water, can change. By measuring sea level precisely with the satellite altimeters and also using the GRACE gravity measurements, similar to Goche that Volker was talking about, to measure the mass changes in the ocean, we can see quantitatively that the mass equivalent changes in the ocean only account for about 1.8 millimeters per year of the observed 3.2 millimeters sea level rise. So the rest must, and this is confirmed with profiling Argo floats, the rest must be due to, in fact, changes in ocean density. That is, the upper ocean is heating up, it's expanding, and that's contributing about 1.4 millimeters per year of the observed sea level rise globally. Volker pointed out that we can make measurements with microwave instruments, and we have been doing it from scatterometers, actually, from KU and C-band scatterometers of sea ice extent in the Arctic and ice thickness as well. Cryosat makes a more or less direct measurement of ice thickness. ICESat-2, following on to launch in the 2018 timeframe, will also be able to make measurements of sea ice thickness by doing the comparison between ice heights and lead heights. But we can see that over time, from the scatterometer measurements, Arctic sea ice has actually decreased in extent. That's what the graph shows here. But as Volker also pointed out, the thickness of the Arctic ice, represented by the multi-year fraction, has also been decreasing. And I pointed out in my earlier hyperwall talk, this is really important because the modulation of thick ice is owing to ocean processes, whereas the modulation, the control of first-year ice, thin ice, is owing to solar insolation, essentially cloudiness. So in the one case, thin ice, we're talking about atmospheric control. With thick ice, we're talking about oceanic control, and it's this switch in the control mechanisms that leads to such concepts and manifestations as climate tipping points. We have the ability to make those measurements, and that form the basis for the research that we're doing. GRACE, by the way, also by measuring mass changes, can measure the changes in water storage in undersurface aquifers. And pretty much globally, we see that in major aquifers around the world, here I'm showing as a time series from GRACE, the sort of northern Indian region, we see that we as a species are pumping water out of aquifers for all good reasons, for human consumption, for use in food supply, as Volker pointed out, but we're pumping this water out at an unsustainable rate. It may take 1,500 years to fill an aquifer. We're pumping them out in 100 years or thereabouts. From the satellite measurements, we can look globally and calculate the decreases and increases, the change in water storage in aquifers throughout the globe. We have an international constellation measuring for the first time with accuracy precipitation over the entire globe. It's anchored by, but not solely fueled by, the US NASA JAXA Global Precipitation Measurement Core mission. Coupling that with measurements of soil moisture and ocean salinity, which we are making now from the SMAP mission, and previously ocean salinity we were measuring also from the Aquarius mission, we could start to put things together. It's not a giant leap to watch where it is that it's raining on the land and then looking up and seeing that, in fact, you have increased soil moisture after it rains. This is a real breakthrough. But then you have increased outflow, for instance, from the Amazon, which leads to decreased sea surface salinities. You can see regions where it doesn't rain very much, close to here, and during the summer, of course, the Mediterranean surface salinity increases a lot. By making measurements of multiple variables, we can understand why and not just what. These measurements are being used operationally in the US for things like drought monitoring. They're being used by a number of organizations, including UN-based organizations, to actually make estimates of food security, of crop health throughout the world. By we as space agencies contributing these sorts of measurements, it contributes to an open and transparent situation in which everybody can understand the state of food crops around the world and the prognosis for them. And so we don't get into this fighting as we had in the early 70s, perhaps, where one country starts to buy up all the wheat, for instance, because they think that, that crops around the world will be failing. We're using, NASA is not at the moment flying a synthetic aperture radar mission. We hope to with the Indians in the 2020, 2021 time frame at L-band and S-band, but we are helping to analyze measurements such as the ones that Volker talked about, also from our colleague JAXA satellites, in terms of providing information for disaster response and mitigations. This, an example from the Nepal earthquake. Of course, in the last 4 days or so, we've had major earthquakes in both Japan and Ecuador. And finally, my last chart, I want to give one more example of how making multiple measurements from multiple satellites of different quantities can tell us the why and not just the how. We talked earlier on about the fact that the altimeter measurements told us with precision that global sea level is rising by 3.2 millimeters per year on average. But what happened in 2010 and 2011? Those who were looking at the chart previously saw that in a one-year time frame, global sea level actually dropped by 5 millimeters. Okay? That's like almost 2 years worth of the mean rise. The question is, well, we know that that happened. The question is why. From making measurements of precipitation, which at that time we had with the joint NASA-JAXA tropical rainfall measuring mission, we see that there are some key regions during that time where precipitation was anomalously high. By making measurements of sea surface temperature and regional sea level variability, we knew that the transition from 2009 through 2010 to 2011 was a transition from El Nino conditions to La Nina conditions. That leads to decreased upper ocean temperatures and a contraction of the sea level. But actually, that contraction only accounted for 40% or so of the observed drop. It was the increased rainfall over land leading to excess soil moisture and groundwater, which actually closes the hydrologic budget of the Earth for that period of time. So through the satellite measurements, we see that that 5 millimeter drop in sea level was actually the result of transferring water from the ocean to the land through the precipitation cycle. And it showed up for such a long time, in fact, because in part, a lot of the excess soil moisture was over Australia, and Australia is sort of shaped like a cup. So water, when it falls there, doesn't run off back to the ocean very rapidly. It's actually a several month to a year process as opposed to all the other continents. Those from Australia can take pride once again in your uniqueness. So to sum up, we are in a situation right now as space agencies, and NASA is pleased to contribute, where we are able to measure, to understand, and to deliver societal benefit regarding our Earth as an integrated system. Thanks very much.
Many thanks, Mike. I think we have time for one quick question for you, very specific question, if there is any.
Hearing none, let's go on to others.
Okay. Thank you very much. So we can move on. And from the Earth, we move far away to the Heliophysics System Observatory. And the talk will be given by Eric Posner in a few seconds, just to need the system to do the job, first of all.
So sorry for the delay. We had to upload this talk recently. So I'm Eric Posner. I'm working with Steve Clark as the research and analysis lead, and I'm a program scientist for some of the missions of the Heliophysics System Observatory, including ACE and Voyager. And I hope my talk will finally come through. So heliophysics is the science of the sun and its interactions with the Earth and the solar system, including space weather.
Yes.
If you go to the next. The Science Mission Directorate has 4 science divisions. You heard from Mike Freilich on Earth Science. I think that's the largest one. We heliophysics are the smallest one. I mention all these divisions in the directorate because heliophysics plays a major role because it interacts with all of them. So we touch on all these divisions in Earth Science, for example. We look at the interaction of the plasma environment with the upper atmosphere. We also look down, but we haven't talked that much about it yet, so maybe that was helpful. We will be launching a couple missions in the Explorer program, ICON and GOLD, that will enhance our presence of looking into that region. And what we will see is that there is forcing from both ends, from the sun and also from the lower atmosphere and the stratosphere, so that's a very complicated system to look at. We also take advantage of planetary science missions. For example, there was a particle instrument on the Curiosity rover that has measured a handful of solar particle events and cosmic rays on the surface of Mars. We touch on astrophysics because they, of course, look at the number of stars in the universe. We look in detail at one, and some people say it's the only one that really matters, that we can really investigate in detail from its core through helioseismology to the outer edges of the solar wind dominated regime where it interacts with the interstellar medium. In heliophysics we have 4 major programs. 2 are intended to for the development of our strategic missions. That's Living with a Star, in which we currently develop in cooperation with ESA the Solar Orbiter mission. And as you probably are aware of, also the Solar Probe Plus mission, which will really go very close to the Sun. So far the closest spacecraft has been Helios at about 70 solar radii. The Solar Probe Plus mission will go much closer to inside 10 solar radii, really touching on the processes going on in the corona. The Solar Terrestrial Probes missions, we just launched the Magnetospheric Multiscale mission that looks at the process of magnetic reconnection that is omnipresent in the universe, that is responsible for most major eruptions on the Sun through flares and CMEs. And we will look into the region of where the solar wind magnetic field interacts with the Earth's magnetic field. There is a reconnection going on. This 4 spacecraft mission will have a tetrahedron formation and look into the most likely regions where this occurs with high precision instrumentation. Then we have the Explorer program. I mentioned Icon and Gold. These are currently under development, but there will be a new AO. I think a draft AO has been released earlier this year, coming up, which gives opportunities also for the international partners to collaborate with us on their missions through missions of opportunity. And there's of course the research program that we use to exploit the vast amount of data we get from all our 18 missions and to get a better return of the investment that we made in creating all of them. And all these programs are used to solve fundamental physics problems in the heliophysics system, to build the knowledge and capability to, at one point, have a more reliable forecast of space weather and to look into the nature of our home in space. I'll have a movie that shows one of these solar eruptions here on the east limb. This is an SDO movie with a 1-minute time resolution. Now we look a little further away, so this eruption then propagates into the solar wind, and if a planet is in the way, it will have some effects on that environment. This is the outside view from the SOHO, the ESA-SOHO spacecraft with a US instrument on board LASCO. So the reason for having so many missions operating at once is similar to what Mike talked about, this interaction of the various components of the Earth system. We also have that in heliophysics. Of course, you saw the CME that propagates into the heliosphere. We want to see it from various sides. We have the stereo mission and SOHO to triangulate where these things are going. We can forecast where they go. Then we want to analyze how they interact with the Earth's magnetosphere, not only the reconnection process, but all the other processes that go on that lead to effects such as the aurora or detrimental effects that affect the power grids or operating telecommunications satellites, for example. And we also help the operational community out with real-time data so they can use the measurements of our fleet that is then transferred to the ground in real time for forecasting or nowcasting these effects. And I want to point out, for example, ACE is located at the L1 point, similar to Discover, where it measures solar wind structures before they encounter the Earth. About a 1-hour advance warning is provided by ACE. SDO, of course, gives us high precision solar measurements also in real time. And the Van Allen probes, following the origin of heliophysics, which we date all the way back to Explorer 1, when it discovered the radiation belts in 1958. It's a follow-on mission to that, and we renamed it after its launch in honor of Van Allen. And they also provide real-time updates of the strength and intensity of the Van Allen belts. These are not all missions with real-time data. Also the Voyagers, I want to point that out, although it's not that relevant for real-time forecasting at Earth. The data that we receive takes 18 hours to reach us at light speed. because they are at the interstellar boundary. Voyager 1 crossed into interstellar space in 2012, and Voyager 2 will follow in the next 3 or 4 years, presumably. We also have a large number of international partnerships. Let's point that out. This is, by the way, not a complete list. SOHO, I mentioned that before, is an ESA spacecraft with instrumentation from various nations on board. The Solar Orbiter is still in development, will be launched presumably in 2018. Hinode and Geotail are JAXA spacecraft with major US involvement. Gold is a partnership with a private telecommunications company, also international. And what is not on the slide here, it's a major omission. MMS has involvement from the Austrian funding agency. They provide active spacecraft charging control that is very relevant for making high precision measurements of these critical regions in the electron diffusion region. Now, the wealth of measurements that we get from the Heliophysics System Observatory led to the development of many, many models across the whole system that goes from the Sun to the heliosphere, into the magnetosphere, all the way down to the ionosphere-thermosphere region. They are all hosted at the NASA Goddard Space Flight Center at the Community Coordinated Modeling System. It has several parts. One of them runs these models in real time, mostly in lower resolution. But the modeling community can also use these models to do test runs, and the CCMC works with all the scientists with the community to help them test and improve on these models. Let me point out one of these. What does it not move? Can you help with that? To the next slide? I don't know. Okay, so this is an example of our collaboration with the National Science Foundation in the research program. We work together with NSF and other funding agencies to allow larger modeling awards that leverage their and our assets. And this is just a list of recently funded awards in the LWS Strategic Capability Program that will run for 5 years and advance several areas from the Sun to magnetospheric science to energetic particle acceleration. This here is a simulation, a visualization of one of these models of the solar wind as it flies by the Earth. While a coronal mass ejection is approaching, and you see there's this deflection around the Earth happening. Now that the CME hits, you see it even more clearly, and that of course is caused by the presence of the Earth's magnetic field. And when the CMEs hit, what happens is reconnection. Here is the visualization of the field. At the poles you get strong effects that are visible from the ground sometimes. That's the aurora, and that will come in, I think, the next movie. This is the aurora as seen from the International Space Station. I was told it is near the coast of Australia, so it's a southern aurora. It's quite a spectacular view. Of course, space weather also has detrimental effects that one has to be mindful of. Space weather has been recognized by the nation and by the White House as one of the major hazards, along with earthquakes, with tornadoes, floods, and other things that fall mostly into Mike's earth science realm. But it's also on par of that now, and we're developing a strategy, and I'll talk about that later. Just one example of space weather effects, or one of these models given here. If you have one of these CMEs and flares erupting, there's always a danger that energetic particles are created and they propagate at their own speeds to Earth. Always at the onset of a solar particle event, you see electrons first, and you can use this as an effective way, because they travel at light speed, to forecast the more hazardous ions that come later. Not only do they have a speed advantage over the bulk of ions that are at about a quarter of the speed of light, they also test as test particles the magnetic connection to the flare or CME site, And that is something you cannot otherwise gain with any amount of spacecraft in the area. So they are very, very useful this way. And about half an hour later, the more hazardous ions come, but having this half-an-hour warning would help, for example, human explorers walking on the moon to get into a sheltered place and to avoid being exposed to a part of this radiation. Of course, there's also galactic cosmic radiation that one has to be mindful of that has more long-term effects. Now, talking about the research program I mentioned before, we have a research program to exploit the wealth of data coming from the Heliophysics System Observatory to address all these major research thrusts in our area. On top of providing awards to institutions across the nation, we also host for the directorate the Sounding Rocket Program and the recently established CubeSat program that all divisions, including us, take advantage of in order to A, advance instrumentation to the next level for future strategic missions, B, do science themselves, and C, even go to places where you could not otherwise go with spacecraft necessarily at even lower cost. So, as I mentioned before, a new space weather strategy is currently under development that came out a few months ago. Currently, various agencies are working on implementing the Space Weather Action Plan. There's a very firm deadline of, I think, the end of this month. There are 6 strategic goals that have to be addressed, and NASA leads the one that is on international cooperation. And Steve wants to point out that we are very interested in working with the international community. We need you as much as you probably want to work with us on this. For example, downloading the real-time data requires the presence of downloading station around the globe, because if you park something at L1 or L4, L5 at these stable positions that are critical for space weather forecasting, we don't always are in view of these locations. So we form a downloading station. The Deep Space Network is a good example. We have stations in California, but also in Madrid and Canberra that help us with downloading this data, but there are also smaller dishes for real-time data that are that download data from, for example, the ACE spacecraft and others in real time. So this is more details about this goal 6. So, for example, we want to help to build international support at the policy level for acknowledging space weather as an issue that affects many, if not all, nations across the world. Increase the engagement with the community on observing infrastructure, data sharing. I think heliophysics was one of the early divisions in NASA to make all data public. All data we create will be put online as soon as possible for everybody to use. We have various data centers, the Solar Data Center and the Space Physics Data Facility. We also want to strengthen international cooperation on space weather products and services, these models that I mentioned, a few examples were given here, and promote a collaborative international approach to preparedness of these events. These are some of the examples that heliophysics currently engages with. Here in Vienna, the UNCOPIUS meets, I think, every year, and we always have a presence there to talk with our partners on future missions, for example, and these are just some other ongoing activities we have. And with that, I leave you with the thought that Steve wants to convey to the EGU as well. Thank you.
Okay, thanks a lot for your news from the sun. We have a little bit of time, so if one question is coming from the audience, I would be happy to take it. Okay, one is here.
You mentioned that the National Space Weather Strategy, NASA is taking care of international cooperation. For the other topics, who is taking care of the actions? Are there other agencies? Or?
There are other agencies involved. It's DoD is involved, of course. NOAA through their Space Weather Prediction Center is involved. I think the FAA, because they care about radiation on polar routes that connect us with areas in Asia, for example. They want to have timely warnings of that. So they're all All these agencies are involved in that. USGS, because geomagnetically induced currents depend a bit on the structure of the conductivity underground, so they play a part in that as well.
Okay, I think we have to keep some questions for our discussion panel, so we'll have a longer break. This is really good news. So enjoy a coffee, and we will convene at 3:30.
Session with the talk of Luigi Colangeli from ESA, and he will talk about the present and future solar system missions.
Okay, thank you, and good afternoon, everybody. So I will give this presentation, of course, on behalf of my director of science in the ESA program, Alvaro Jimenez, who could not be here today. And the goal of this presentation is to give you a bit of an overview where we are with the science program, how the science program fits in the system of the European Space Agency. I'll go through some information about a few missions. Of course, I will not be able to cover all the missions that we have in place in science, in particular for the solar system, but I will concentrate also on what are the future opportunities, because I think these events like the EGU are a perfect opportunity to inform the communities that perhaps are not yet fully involved and engaged in space activity, and therefore to draw their attention into these opportunities with their ideas. So about the science program, to complement something that was said before, let me recall that we have at the present time 22 member states part of the European Space Agency. 20 of them are members of the European Union, and we have other countries, 7 countries at the moment in Europe with which we have cooperation agreements. Canada is also involved in our activities in a number of programs under a long-standing cooperation. Of course, this is a beauty of our program because it allows all the Europeans to collaborate on missions that have medium and large-scale calibers, but at the same time includes a number of, let's say, challenges to have the cooperation properly driven and properly carried on to satisfy not only the scientific but also the programmatic interests that are relevant in the different member states. Another feature that I want to mention is that ESA covers a huge set of different areas, one of which is, of course, the space science, so that the complexity of the system is also in the way in which the different programs have to interact and work in synchrony in order to have the European system working cooperatively for the success of these projects. But let me say the peculiarity of the science program, because the science program is what we call a mandatory program. It means that all the member states cooperate and provide support to the program with a proportion that is related to the GNP, their national GNP. It means that science is a sort of stable support from the different member states, and this allows the science program to build a program that is based on the medium long-term planning. All the other programs are instead what we call a la carte projects. That means that every time we have to go in front of our funding agencies in the council, they have to subscribe to these programs according to their interests in science, in applications, and whatever. The other important thing of the science program, this is some way obvious for the community that is in this room, they must be science-driven, the program must be science-driven, and therefore it must rely on the support of a broad community and must rely on a selection process that is a peer review process in which the ideas are compared and eventually selected based on the excellence. Let me give a little of overview where we are with the science program at the present time. This is what we call the ESA fleet in the solar system. And let me say that in this chart you see missions in which ESA is leader, but also missions in which international partners are leaders and we cooperate with them. So I don't go into the details of all of this, but certainly Cassini-Huygens is one of the cases in which NASA is the principal element of the mission, and we cooperate with them still today for the Cassini orbiter, and in the past with the delivery of the Huygens lander. Let me also show a similar chart for what concerns the astronomical side of our program, where we have missions covering different spectral ranges, and I'm happy to report all these missions because many of them contribute to understanding better the behavior of our solar system. So this dichotomy between planetary science and astronomy to me is not relevant. It's important to have excellent science in which the communities cooperate together and achieve the best through the tools that are available in the science program. Let me recall a few, let's say, benchmarks in our program. I mentioned before Cassini-Huygens. Huygens, as far as I know, is the lander that was successfully landed in the most far place of our solar system in 2005. So this is really a record for our agency. And certainly Rosetta is the other record after around 10 years from that success, in which we have been able to rendezvous, orbit, and soft landing on a comet through the different elements that are part of the Rosetta mission. Another mission that I wish to recall is Cluster. Again, another mission in which ESA and NASA cooperate, for a couple of reasons. First of all, because this mission is delivering, since the time when it was launched in 2000, excellent science in a number of fields, and because this was the first time to have really a network formation of spacecrafts flying in the solar system and looking at the phenomena that otherwise could have not been discovered in 3D vision. Nowadays, we have some tool to joystick the four spacecrafts and really put them in close flying formation and detect processes that otherwise could not been detected. But I want also to recall that this mission, in a sense, is also related to the exploration of the interaction between the solar energy and the solar particles and our planet. And in particular, Cluster and Swarm, that was mentioned before, collaborate a lot in order to explore phenomena that at different distances from the planet, our planet, are relevant. And there are papers coming out using data from Cluster and Swarm. Gaia is an astronomy mission, but I wish to recall about it because it's one of our key missions, cornerstone in a sense, because it aims to detect and explore with astrometry, spectroscopy and photometry 1 billion stars, and the work is ongoing quite at a good pace, and we will have already this summer the first issue of a catalog coming from the mission. So it's working perfectly fine, and certainly is a success for the agency that we need to recall. The other success, a very recent success, is the launch of the LISA Pathfinder mission. This is a mission that is a technology demonstrator. It's not a real, in quotes, science mission, because we want to test with this mission a number of technologies like inertial sensors, interferometry, drag-free systems, and micronewton propulsion technologies that will have to be used for future larger mission in order to detect gravitational waves. And this subject has become very recently really a very relevant subject in the scientific community at large, with the detection of gravitational waves with ground systems. So certainly the expectation on LISA Pathfinder is, on LISA, or whatever will be the name of the mission coming out in the future for the large mission number 3 in our system, is enormous. And thanks to the success of LISA Pathfinder that we have now living, certainly it will be possible to put in place a prime also in this area of the science exploration. Well, going back to our solar system, ExoMars now is a reality. We have launched recently the Trace Gas Orbiter and the Schiaparelli demonstration module. It's a mission that is part of the robotic exploration program in our ESA system, but certainly it's a huge, interesting mission from the science side. So it's a really merging of technology demonstration and science objectives. It's a mission in collaboration with the Russian Roscosmos agency. So it is now, for what concerns the 16 mission, on its way to the planet. As far as I know, the different checkouts have been successful, so all the elements and the instruments are working fine, and we hope to see in a few months from now the delivery of the entry, descent, and landing module on the surface of Mars in October, if I remember well. And then the next step will be the ExoMars 2018. There we know that we have problems with the actual launch date. There are works ongoing to see if the 2018 can be maintained or it has to be shifted to 2020. Is a work ongoing right now. But certainly it will be an excellent new enterprise for ESA and Roscosmos, because we will be able to put on the surface of Mars a penetrator, a driller, able to go down to 2 meters under the surface of the planet for the first time and collect samples that have to be studied with the laboratory that we have on board our rover. There will be also a surface platform equipped with the payload, and this is a responsibility mostly of the Roscosmos part, but the instruments are shared on both sides for best achievement of the scientific objectives of this mission. Baby Colombo is the other flagship mission in our system, because it will visit Mercury after the successful MESSENGER results from NASA. Certainly this mission, that is a collaboration with JAXA, and it has two spacecraft, a Mercury Planetary Orbiter, that is essentially the contribution from ESA, and the Magnetospheric Orbiter, that is essentially a contribution from JAXA. We will really be able to explore the system of the planet and the environment around the planet in a way that some way will provide a quantum jump in the knowledge of this planet after we have learned a lot through the MESSENGER mission. And this is expected to be launched in 2018. Well, I mentioned Rosetta, but I cannot avoid to go back to it because 2016 will be really another benchmark in this mission. As you may know, the mission has been extended in operations until September this year. That means that we will have data along the inbound and outbound legs of the comet, and therefore compare the behavior of the environment and of the nucleus along this path. But at the same time, what we plan to do to complete this mission is what we call a soft landing on the nucleus of the comet with the orbiter. So it will be, at least from the public outreach point of view, certainly another interesting achievement. By the way, we will have the opportunity to retrieve scientific data also during this process, power conditions permitting. And then this is what we are living at the present with the science program. Let me talk a bit about the future, because here we enter the area in which we have calls, open opportunities for international collaboration in new initiatives. So certainly the community globally that is part of the EGU should be interested in these opportunities. Let me recall again what I said at the beginning, how the system works in our selection for scientific missions. It's a bottom-up approach in which we have a science advisory structure with a Space Science Advisory Committee and working groups relevant in the different fields. And the role of these groups, and anyway, the Space Science Advisory Committee, is to advise the executive, the director in particular, about the missions or the concept to be studied and selected. But let me stress again that the decision is taken by the Science Program Committee, where all the member states sit. And let me recall that each member state has one vote, and therefore the decision is really a very democratic process in which everybody has to express it's their position. So this is the process in which we select missions for study, and we select missions to be then put in our system for future opportunities. So what are the elements in our program? We have what we call large missions, and they in some way involve a budget of the order of 2 years of our yearly budget. Let me recall that we are at the level of, at present, 550 million a year. So this is the typical missions that we consider our flagships. And according to the profile of our funding scheme, we can expect to have one of these every 7-8 years. And they have to be innovative, certainly, and they need to bring the European scientific community to be leaders in the fields in which these missions are selected. Of course, they are open to collaboration with international partners, but in this case, we expect a sort of junior partnership in the participation to these missions. The other element are the M missions, the medium-class missions, where instead we introduce flexibility. This means that in this case, we are completely open to any kind of collaboration, provided there is a leader for the mission, also with international partners. So in this case, the mission budget can be used to contribute to a mission led by another funding agency, or it can be a joint effort with other funding agencies. And again, in this case, the cost is around the value of one annual budget. So the cadence that we can, at the present time, afford is of the order of 1 every 3-4 years. We have other elements in our program. A new element was introduced a few years ago that's called the small missions. It has been a process in which we have selected for so far one case. It's a very little amount of budget dedicated to this case, and in principle is led by national agencies in our system. Missions of opportunities instead are cases in which we contribute to missions led again by other funding agencies, but at a small level, the same order of magnitude as the small missions at maximum. An example recently has been IRIS mission, in which NASA is leader, and we contributed to a minimal part to the operations of this mission. And in this framework, we had the opportunity to involve European scientists in a relevant role in the operations and in the science of this IRIS mission. Let me just mention James Webb, because it certainly is a huge enterprise in which all the major funding agencies in the world, NASA, ESA, and the Chinese agency are involved. For ESA, the involvement is at the level of a medium mission. I want to recall this because this is a typical case in which a medium-class contribution allows European scientists to be partner and active partners in a mission that's really a major world enterprise. And therefore, keep in mind that this is a way in which you can contribute with international partners to be really active and actors in these opportunities. Well, let me go quickly through the missions that we have now recently selected for the future. First of all, the large missions. Now you know what we talk about. The first large mission that we have selected is JUICE. I don't think I have to spend more time to go in the details because there are sessions dedicated to these fields. So JUICE is the Jupiter Icy Moon Explorer. It's a mission in which ESA is a leader, of course, as we said, for a large mission, but we have a collaboration with NASA. They are putting on board an instrument, and they contribute with key elements for other two instruments. So certainly is a way in which we like to collaborate with partners to achieve the best return from our investment. Let me recall JUICE as a sort of second step with respect to Cassini. What we are living today for Cassini, with this fantastic tour of the Saturnian system, in a few years from now, I hope it will be the same with JUICE for the Jupiter system. So keep in mind this parallelism. And the second large mission that was selected recently in 2014 is a large X-ray observatory. It's the way in which this mission was selected was through a call for white papers, and after that two scientific fields were selected. One is the hot and energetic universe, and for this one in 2014 then the mission was selected. It is now under study, And this will be another relevant area in which ESA wants to play a major role. Again, also here discussion is ongoing with NASA and other partners to eventually contribute to the mission. For what concerns the large mission number 3, the scientific team, I said before, has been selected, the gravitational universe. For this mission, at the present time, we don't have yet a mission, in quotes, selected, but certainly the field is pressing, and the scientific community behind this field is pressing a lot to go as fast as possible to have a mission in this area. There has been an advisory team put in place, and at this link you will find the final report that has been published a few days ago. Going to the medium missions, well, Solar Orbiter was mentioned before. It's a joint ESA-NASA mission. The launch is October 2018. You know perfectly that this mission will introduce the innovative approach of having at the same time remote and high-inclined and in situ measurements. So certainly it will be a jump in our knowledge about the processes that occur in the Sun and the connections with the heliosphere. The mission number 2 in the medium class is Euclid, that will study essentially dark matter and dark energy. Also here we have advancement in the mission development with the launch plan in 2020, and here we have contribution from NASA. And the M3 mission is Plato, that is an exoplanetary mission, therefore a mission that for sure is interesting from the planetary community, in which we will detect and characterize Earth-like planets with small masses so that we will be able to really identify the key planets that are available around bright stars. In this mission, of course, it will be necessary to involve also ground-based observations because there is a lot of need to evaluate false detections from Plato and at the same time do radial velocity measurements to allow the characterization of the planets. And we are working on this mission that has to be adopted probably later this year. The small mission I mentioned before is an enterprise led by the Swiss Space Agency in collaboration with a number of other space agencies in Europe, and in which ESA is partners as well. In this case, the mission is not devoted to discover new planets, but to look at planets exoplanets that have already been identified, but focus on the characterization of their properties. And finally, let me recall this new opportunity that we have just launched with an open call again for a joint mission between ESA and China's Academy of Science. SMILE is the winner of this competition. It's a solar wind magnetospheric ionosphere link explorer. The process has been built in order to have, since the beginning, a joint approach in the proposal of missions from the community. So it was requested to have proposals from joint team from Europe and China. The selection process was run jointly between ESA and the Chinese Academy of Science. This mission has been selected and now is under development. So this is a sort of summary of what I've said so far. So let me say that for the Cosmic Vision process, starting from 2011 until now, we have done a lot of bookings for the future for new missions, but we continue to run and to maintain the same pace for the future. And therefore, we recently ran a selection for M4 candidates, the 4th mission in the M program. And there are 3 missions at the present time under extended study. One is again an exoplanetary mission, a plasma physics and X-ray mission, and we plan to have next year the down selection of 1 mission for advanced study. The present then, we have an M5 call coming soon. So I know that many teams and groups and scientists in Europe, and also in collaboration with international partners, are looking at this opportunity for being active and possibly being selected. We already ran in last year a sort of pre-call in which we asked the teams to come with their ideas. We had an interaction with them to some way pave the floor for this call to come. Now the call is again under preparation. It will come out in few weeks from now, or perhaps days. I cannot be more precise. The work is ongoing right now. And we expect that these communities that are sitting in this room will come with their bright ideas to be competitive and possibly winners. Of course, it's an open competition where all the communities, planetary physics, magnetospheric physics, astrophysics, and fundamental physics will run their show. A final point is something that we have launched very recently, is an announcement for new science ideas. So it's not, in this case, a call for missions, but really for new, bright ideas that want to access to space for implementation. So we don't ask in this case that people submit their proposals with a clear description of their payload, of their spacecraft, or their operations, but they have to come with new ideas. That means that we hope not the usual communities that are ready to compete for M missions, for example, will be the actors in this case. We want to really trigger the interest for other communities that perhaps have, again, good ideas, but they don't know how to access space to do to take this opportunity to come and bring their ideas for selection. Again, it's a competitive approach. The call has been released in February. Letters of intent are due by May, and after that we will go through a selection process of these ideas, and the ones that will be selected will be studied by ESA in cooperation, of course, with the proposing teams in order to be sure that this may evolve towards something that can become mature in a few years from now to become a competitor in future M-class call. So it's not changing the rules. It's a new line in which new communities can come and grow with us, with ESA in the science program, to make their ideas real. So it was mentioned before, we have a very important appointment this year in December. That is, the Council will meet where all the member states sit together and some way decide what is the future of the different programs. In the case of science, at the last ministerial conference, it was in 2012 when science was discussed, we obtained a stable funding profile along the 4 or 5 years of the work without inflation compensation. So in a sense, our purchasing power in the past years has decreased. Fortunately, or unfortunately, depending on the points of view, inflation has been very low in the past years, so this didn't affect our sequence of missions. But certainly what we would like to see at the next ministerial conference is a restorage of this compensation for the inflation and eventually additional funds in order to maintain the pace on the missions with these calls and eventually introduce new features in the program for having diversity in the different fields that we can cover. So that's the hope, and that's the area in which certainly the community can help the science program to become solid, more solid, or continue to be as solid as it has been so far. And I stop here. Thank you.
Thank you, Luigi. We can have 1 or 2 questions if there are urgent questions. Otherwise, you can ask your questions to Luigi and the other speakers during the discussion at the end of the session. So I see that there are no questions. So thank you, Luigi, again. And we'll proceed with the next talk. Unfortunately, James Green couldn't come, but instead Jim Spann will give the talk on NASA's planetary science missions and participations.
All right. Let's see. Just press the button and advance it. Scroll also. Okay. All right. Thank you. Appreciate the opportunity to visit here. Jim Green sends his regards. Unfortunately, he was not able to make the trip, and so he asked me to present for the planetary division up at headquarters, NASA headquarters. When Arik Posner presented earlier, he mentioned that there are 4 divisions at NASA headquarters. And so this is one of four. Mike Freilich leads the Earth Science, and astrophysics is led by Paul Hertz, and Stephen Clark leads heliophysics. And so I'm going to focus primarily on the planetary missions. And this is basically the portfolio of the Planetary Science Division. And you can see that it's basically divided up into two parts. One is basically essentially touring the solar system with various destination missions, and then the other one is the Mars program. And the way I want to present this talk is that I want to talk about, I want to separate these two parts out, and then within each part I'm going to talk about the strategic missions, which are typically decided at an agency level, be it led by NASA, or NASA is a partner with ESA or JAXA or some other agency. But those are strategic and tend to be larger missions, and even though the contribution may be smaller, and that contribution is competed, it's decided at an agency level. And then there are the principal investigator missions, which are much like the smaller ESA missions that was just mentioned now, where it's open to the science for the principal investigators to propose an entire mission. And then those are selected where the principal investigator is essentially responsible for those missions. Again, there is a lot of international collaboration on those missions, but it is a different type of class, and typically those are a little bit smaller in toto compared to the strategic missions. So that's a little bit about how NASA works. So these are the missions that that are circled here that have international participation, be it ones that are led by NASA or led by other missions. And I'm going to really focus only on those missions. You can see there are a few other ones that don't have a strong international collaboration. And it's not coincidental that practically everything that it's circled here you've already heard about. And that really highlights the fact that as we explore the solar system, no single agency can really do that. We really do have to depend on each other, especially as we get more ambitious in terms of the capability of the mission and the technologies involved. Identifying the best people across the planet to do the work is really the way that we can be successful. And so I think as you go through here, it may seem to be a repeat of a lot of things that have already happened or that you've already heard about. So the first one that I'm going to talk about here is the Cassini mission. And this mission has really been kind of a postage stamp for international collaboration and success and longevity. It's been extended twice. The first time it was extended after the prime mission. It was extended further, and they called it the Equinox mission. And now it's going to go into its second extension, and that's going to be called the Solstice mission. And that's kind of its swan song, because at the end of that mission, through all of its successes, including the Huygens probe, at the end, you're going to see Cassini fly by between the inner rings and the surface and make some daring maneuvers as it ultimately enters the planet's atmosphere, taking data all the time. And that'll just be a fabulous mission. Again, this is a heavily leveraged mission between with the international community. The second I'm going to talk about is the Rosetta mission. Again, we've already mentioned this. This was the fabulous mission landing on the comet, and there are several instruments on that mission. NASA is a minor partner on 3 of the missions, and to me, this was just one of the more fabulous discovery missions of all time, landing on something that the public identifies with the comet, but now we've actually seen it up close and personal. The next one is the JUICE, the ESA JUICE, the Jupiter Icy Moons Explorer. Again, this has many instruments, 11 instruments from 15 countries. NASA's role is we're going to lead one instrument, the UV spectrometer, and then we have hardware on 2 of the other instruments. One is the RIME, the radar for the icy moon exploration, where we will be able to look at the subsurface using the radar, and that's a joint development with NASA, University and the University of Trinto, and JPL, where US is providing the radar hardware. And on almost all of these, the international science team has partnerships from everywhere. Then on this mission, there's the particle environment package called PEPI, which has two components, and you can see the significant listing of participants. The colorful flags indicate how international it is, where it's really led out of Sweden, but has two co-Is from Switzerland and then from the US. The two components, one really looks at the neutrals and ions, and the other one looks at the energetic electrons. So those are the strategic missions that I was going to mention. Now I'm going to go into the principal investigator program. One of them in the planetary mission is called the Discovery Program, and here you see several of these missions that many of you probably participated or certainly know about that have been completed. And but then I want to highlight the four here that are in progress right now. Dawn, the Lunar Reconnaissance Orbiter, the Bepi Colombo, and the Mars Insight. So on the Dawn instrument, basically it has three primary components, where the international collaboration on the two cameras, the spectrometer and the camera, were critical for the success of that. The US provided the gamma ray and neutron spectrometer. On the LRO orbiter, there were 5 primary instruments, one of which was provided by the Russians, the lunar exploration, the neutron detector. This mission had a lot of innovative technologies and drew a lot of attention as it works. Doing different things. One's looking at the surface and the interaction of the moon with the solar wind, but then also looking at the impact of space weather and those particles with human tissue type of materials. The next in the Discovery mission, even though this is an ESA mission, the Bepi Colombo Mercury mission, one of the instruments was competed through the discovery process, and that's the Strophio instrument on this ESA mission. The last mission I want to mention is the interior exploration using seismic, geodetic, and heat transport. This is a Mars lander mission which has a significant component of international participation, as you can see by the logos on the side there. On InSight, this mission has 4 primary instrument packages, 2 of which are really led by foreign contributions to NASA, which one is the heat flow properties really out of DLR, and then the SEIS, the seismic experiment and interior structure led by CNES. JAXA's Hayabusa instrument mission is really is one that's predominantly led by the Japanese. We do have NASA has again a small participation role in that. Quite frankly, it's primarily helping them operate that mission, and so as a result, we share certainly in the data, but also in some of the samples as it goes to an asteroid and plans to return some of that. Let me talk next about another competed program called the New Frontiers, and this is a little bit larger than the Discovery program. And to date, we have had 3 missions. I should say have had. There are 3 missions in this program. The first one is the Pluto encounter with, or the encounter with Pluto of the New Horizons spacecraft. The second mission, though, has a strong international collaboration. And that's the Juno mission, a polar orbiting mission, and it was just mentioned right now that the Jovian system is going to be much like the Saturnian system in that we're getting ready to go explore that in great detail with many assets, this being one of them. The PI of Juno is Dr. Scott Bolton out of Southwest. And then on the horizon and that's to be launched this summer. And then on the horizon also is the OSIRIS-REx asteroid sample return mission, which is primarily a NASA mission, but again, that's going to be launched this year. So on the Juno, here's a listing of the instruments with their primary sources, and highlighting the international collaborations from the Italians is the GIRAM mission instrument, and also GS, that component, and then finally the magnetometer down here from the Danish. So now I'm going to shift and go to the Mars missions, and I'll take just a little interlude and kind of do a halfway of a little bit of a promo that on the hyperwall at NASA that has kind of around the corner back here, we're going to be presenting some a presentation on The Martian. Now, how many of y'all have seen the movie? Okay, how many of you have read the book? Oh, even better. The book is always better than the movie. The point I want to make about that is, okay, so the hyperwall presentation is going to talk about the activities that NASA is doing that are seen in that movie, and what the movie got right and what it didn't, and kind of some of the reasons why and why not. But the point I want to make at this point is that, in fact, a colleague, Dr. Dan Baker over here just whispered to me and says, you know, what we really need to do is to have a movie like The Jovian, okay, or you know, The Plutonian or something like that, or, you know, The Mercury Man. So, you know, and that would really do two things. One, it would really enhance the chances of getting our smart young people that are coming through, and I'm talking about those that are pre-teenagers that really get captivated by these movies. And secondly, it would just get the public in general and provide great support. And I have actually a third suggestion that we ought to hijack Hollywood for like 10 years, and all the budgets that they move for the movies, put it into the space program, and we could actually do some of this stuff. But that being put aside, let's talk about the Mars program here. You can see that there are several orbiters in the program that are already up there and on their way, and there are some rovers on the ground. I've talked a little bit about InSight, and let me talk about some of these other ones here in just a second. The ExoMars program, once again, has just already been mentioned. The successful launch of the Trace Gas Orbiter. NASA has a couple of contributions on that, the Electra instrument, as well as the Mars Organics Molecule Analyzer, the MOMA, with the DRLR as lead on that. Again, these cannot, the whole talk here really is highlighting the fact that these really are international partnerships. The Curiosity rover obviously is on its way up a mountain there with many instruments, as you can see here, and most of those instruments have international partnerships, and you can see that these are coming from many different countries, and each one of them, as they bring their expertise, enable this to make this to be a successful mission. For Mars 2020, again, there is some international participation. All of these instruments here were competed, and the Norwegians have won the component on the antenna on the RIMFAX. The French are helping out with the SuperCam mast unit on one of the cameras there, and the Spanish are also working on some of the sensors to measure the environment around Mars that Mars 2020 rover will have. So in summary, I'd like to just indicate that this is not a comprehensive review of all of the missions, but it is one that highlights the role that our international partners play in all of the NASA missions. It's a privilege to have to work in an international environment in this way, such that one, you get to understand and work with colleagues around the world, but also you can assure yourself of getting the best technologies. Even though I understand that international collaborations sometimes are difficult, not because of the science, but because of the organizations in which we work, and nevertheless it makes it worthwhile. So with ESA, we've had, I've highlighted several missions with JAXA as well, and with the Russians. There are many other countries that provide instruments for both principal investigator and strategic NASA missions. And all in all, because of the valuable open data policy, we all participate in analyzing the data. And so with that, I will conclude.
Thank you, Jim. Actually, I would like to maybe suggest that we can directly go to the discussion. And so I would like to invite the speakers to take place at the scene. So, yeah. And I would like to also invite Jonathan, the Vice President of the EGU.
Hello. Of course, I'm not Volker Liebig. He had to. It's okay. Yes, okay. Sorry. So my name is Tommaso Parinello. I am responsible for the CRISAT mission, and of course, I'm not Volker Liebig. He had to leave, so I have to apologize on his behalf.
The rest of the speakers. Yeah. Thank you. We know the rest of the speakers. I would like to give the microphone first to Jonathan.
Well, okay, so I'd just like to say a few words on behalf of EGU. We as an organization are extremely pleased to be running this union session. We're delighted to have senior, if I can call them that, senior management from both NASA and ESA in the same room, on the same platform, discussing missions for which, you need to remember that most of us are reliant on data from these missions for the science that we do. And so I hope you're going to press these people on some of the programs that they're putting together, and we're going to have a lively discussion about the future activities of both organizations and how also perhaps EGU can work more closely with the space agencies, which is one of the things that we really want to try and do, and one of the motivations for this session.
Thank you, Jonathan. Actually, I will leave the microphone here, and I'm going to use this microphone to start the discussion. You want to start with the open questions, or okay? Let's start with. Let's see what the audience has. Okay, we can start with the questions by the audience. Are there any questions? Yeah, Nick is coming already, so. Yeah, you have to walk.
If we can't hear the question, we will just answer what we want. Yeah.
That sounds pretty good to me. I thought that's what you always do. Actually, just a slightly provocative question. Maybe I was asleep when it was mentioned, but what's the current status of the Europa collaboration between ESA and NASA?
Well, I think the collaboration is on. I don't know the details, and this really is a Jim Green mission discussion. I can tell you, though, there are significant plans being put in place for getting the mission to where it needs to go in terms of the transportation. And I don't know beyond that in terms of how the science team is being divided up or anything like that. However, and from the NASA perspective, there is a full commitment to proceed with this, if that's really the nature of your question.
Maybe I can add something on this. Okay, first of all, let me say that this is one of the cases in which I'm glad to report that this interaction started at an early stage. So when NASA started to discuss about this NASA initiative towards an Europa mission. They came to us and we discussed the possible scheme for exploring areas of collaboration. So there have been studies that have been carried out in collaboration by our engineers in ESA, and they are, by the way, now public for the community to use them. Now, this is the, let's say, easy part of the game. The complex part is to see how the two systems, and this was some way reported before, can interact and find the right scheme to collaborate. And certainly on NASA side, that there are processes that are ongoing. I'm not able to report about them, but certainly they have to be taken into account by the teams in Europe that intend to contribute to this. Because on the ESA side, the way in which this contribution can occur is through what I presented before, a competitive process. So for an M, whatever, 5, 6, 7, depending on the scheme that NASA will be able to put in place, we need to have a proposal from teams in Europe. The proposal has to go through the selection process that we run according to the scheme that I presented. And if this is one of the winners or the winner of this competition, the interaction will become a real joint mission. So again, it's a matter of finding the right sequence of events in terms of timing, and sometimes this is difficult, but at the same time, it's a scheme that we need to work together to make it positive and affordable.
Yeah, I think that the basic point that you hear from the US side, and as you probably know, I'm on the science team of Europa Orbiter as well, but there's so much momentum behind this now in the States. It's really moving fast, and it's going at such a rate that ESA would have a hard time keeping up with it because of the various, we know how it is with European collaboration. And so are we looking now at something that's beyond the current NASA Europa Orbiter, or is there going to be some slowing down of that momentum?
Well, I know at NASA it is hard to move too fast, or it's hard to get moving fast. And when it happens, how do we cope with that? I don't know the specific details in terms of, is it going to slow down or whatever. I do know that there is a significant amount of momentum, political support, which leads me to believe that this is going to happen. The details, I believe, as was said, have to be worked out in terms of the who does what, and the timing is probably the most difficult thing at this moment. I'm sorry I can't give you much more detail, and I just don't think that they really exist at this moment. I think things are still up in the air.
Again, if I can add an element there. Of course, when we open a call like the M5, for example, there must be a timing for the selection process. And therefore, if on the international partner side, now this is the case of NASA, but could be for anything else, there is a deadline and a time for a launch that is not compatible with this timeline, of course, this opportunity is not real. So we have to work out with the partner to see if the profile of this mission is one mission or a sequence of missions that can be some way in time divided by a number of years, allowing the team that wants to present something in this competition to be compatible with the timeline that they have in mind and we have to follow.
Understood. Thank you.
Yes, Dima. Yeah. And then you.
Actually, thank you, Nick, because Nick asked the second part of my question. So, and I wanted also to ask about the Europa Clipper. First of all, what is the status of the mission? Because what we hear at different meetings is that, as Nick said, that yes, it's with a good momentum, it's moving forward. And the second question, what Luigi said concerning the M5 calls, this is really large-scale collaboration on the mission elements level. My more specific question is about the collaboration on the instrument side, because I was the study scientist for JUICE, and we invited, actually, there was a participation from the Americans or from the NASA to the JUICE mission, but I have not heard about any possibility for Europeans to be on board the Europa Clipper. So two questions. One of the status of the Europa Clipper, and second, possibility of participation of European instruments on the Europa Clipper.
Well, so I think that the clipper is something that's in discussion right now, and once the specific approach or mission concept has been established and they're going to pursue that, I feel very certain, which has typically been the approach, that participation of Europe in the U.S. instruments is going to be seen very favorably. But again, until the specific design and the plan is laid out, it's kind of difficult to second guess. The wild card in this, or the big question mark, is the strong impetus to really move fast on this is not necessarily compatible with the typical decision-making process that evidently ESA has, as well as NASA. Mm-hmm. And I think that's a little bit of where the start-stop is taking place now. And when I get home, I'm going to call Jim Green up and say, Jim, why didn't you tell me?
Thank you.
I'm just returning from a symposium, a space symposium in the US, where Administrator Bolden reiterated that the priority is now a journey to Mars with humans, so by the end of the 30s. And clearly there are development of big launches, human infrastructure, with a phase also around the moon, cislunar phase. So my question is, from the geoscientist point of view, what are the opportunities that exist? For instance, like we had the human spaceflight program paying for lunar reconnaissance orbiter, a great exploration mission, which then was converted into a science mission. So are there some robotic precursors from this proving ground or journey to Mars where you could have a geoscience benefit for Earth, for the moon, or for Mars?
Okay, thank you for that question. You've just kind of given me an advertisement for, I'm going to give a talk on Thursday, which is exactly the research objectives of the proving ground. The title is something like that. But at any rate, so I am going to talk a little bit about the various things that are being discussed beyond strictly human exploration, and that is kind of a stepping stone to get us to Mars. But there's so much more that we can do. And I don't know if you recall, maybe 10 years ago, a meeting was held in Tempe, Arizona, back when NASA was all excited about going back to the moon. And there's a meeting that was held in which the science that could be done if we were to go back to the moon, what could be done? And we brought all sorts of disciplines together to have that various type of discussion. I could imagine that perhaps a similar sort of discussion in a more broad community-based event or forum could take place, which would flesh out a lot of these things. At the moment, the architecture for the proving ground and then becoming independent of the Earth and eventually going to Mars, that architecture is being established, and part of this study team that I'm on is to ensure that as we set that architecture in place to ensure that humans can get there, that we do not dismiss the role of the robotics, nor do we dismiss the fact that there's an awful lot of exploration science that maybe not even necessarily associated with Mars that could help us, that we could take advantage. You know, some examples are, you know, a far-side radio telescope, telerobotic type of activities. Maybe it'd be a great platform to observe the sun or to do some space weather. So all of those sorts of things are being, even a platform to look back at the Earth, and maybe we don't have to go to L1. Maybe we can get it from the cislunar. I don't, you know. Okay, that's I'm spending his money right now, but so a lot of those discussions are beginning at this point, I should say. Does that answer your question?
Well, that's a good start, because also, of course, from the European side, we look also how human space flight can contribute to Moon and Mars exploration. So we are looking at what Moon Village, about contributing to the Mars journey. So clearly, robotic precursor that delivers science in a defined timeline are very important.
Exactly.
Okay, so I'm Miora Mandea. I'm in charge of Solid Earth Observation Program in CNES. So my question, of course, is Earth observation. I'm just thinking about the presentation made by Volker and the one made by Mike. In Volker's presentation, we've seen some results with Goche and with Swarm, but really presented separately. Mike said, okay, it's really very nice to have multi-dimensional research with multivariables and multi-missions. My question is, what you are doing for Solid Earth in order to have really possibilities to go to these different data sets, which are really different in themselves, but so important to understand what's happened with Solid Earth, because it's solid, but it's pretty dynamic.
No, it's an excellent question about what we're doing collaboratively, if you will, to both provide the data and the analyses of joint data sets with respect to solid Earth. From a gravity mission standpoint, very specifically, Goche on the one hand and Grace on the other hand, when they were originally designed, were thought to occupy not totally overlapping regions of parameter space in terms of temporal evolution and spatial resolution. As it turned out, those missions overlapped far more, thanks to the excellent engineering, far more than they were optimized for. Let's put it that way. We have, in the last couple of years, convened some meetings of the joint gravity research communities with a thought to the future of potentially designing a fully collaborative gravity mission directed at the solid Earth, as well as climate and other things. The teams have not met, I think, for about a year now, perhaps a year and a quarter or so, but it is one of the topics that is on the agenda of the joint NASA-ESA bilateral coordination group. In other areas of solid Earth, the key, I think, is free and open exchange of data for research and not simply for disaster response. There are many different countries who are flying synthetic aperture radars, which operate in interferometric mode and therefore can make precision measurements of deformation and things like that. It is not always as easy as in some other of the earth science disciplines to access that information routinely for scientific analysis. When we do, however, the sum of all of the measurements turns out to be far more. The impact of it turns out to be far more than the individual impacts. So I would look more towards, maybe it's the easy part of it, the policy collaborations to enable free and open exchange of data. And I will point out that it's quite excellent that Sentinel-1 data are being freely and openly exchanged and are being mirrored at the NASA site, as will NISAR data, the L-band and S-band synthetic aperture radar from our upcoming mission with the Indians. So does that answer your question, or do you want to follow up?
Yes, partly, because open data, it's of course a very good reason to say we have access to this data. But what we need also as scientists is how to deal with huge amount of data we are going to have. And it was one of the points with Sentinel program, of course. Also, we have the data, but how we are going to have the computing capacities nearby. So this is the other part of the story.
Okay, I'm not sure that I'm understanding. So we have the data, and are you talking about investments on the parts of the agency in analysis tools
Yes.
and computation,
Yes.
et cetera?
Exactly.
Ah. You want to try it?
Try. Well, what we can say is that, for example, in the next Earth observation program, there is important elements in which we are looking exactly on this in tools, and also we're looking at big data, and of course we're looking also at preservation of the data from the past. And as Mike said, all this per se is very important also for the scientists. So indeed, open science, indeed having data available. So we're looking at platform, for example, for engaging users, so that the data, so that the user do not have to go to get the data, but the data be very close to the users. All this, of course, means resources that hopefully we can put into place in the next program.
Can I just ask a follow-up question to that? I mean, that's great, Tommaso, and I think that's a good initiative. But just this is like a funding model data exploitation question for all of you, actually. So if you look at NASA and ESA and you look at the space segment, there's quite a lot of similarities. You both launch satellites; they both work beautifully. When you look at the ground segment, there are some really fundamental differences between the way NASA operates and ESA. So NASA funds projects to do science, scientific exploitation of the data that they've spent a lot of money acquiring in space. In general, ESA doesn't do that. The STSE, that's the science support to science element, is a rather small budget in the ESA line, and you have a ministerial meeting at the end of this year where there's potentially an opportunity to, and it would be, I think, if ESA wants their data, their missions to have greater value, then one of the most effective ways they can do that is to have greater support for the science yeah. So all of you, do you want to say something about that?
Let me just very quickly, from an Earth science standpoint, explain the NASA approach. NASA Earth Science Division really has as its objectives understanding the Earth as an integrated system and developing and testing applications. The missions are just one part of that. We also have a dedicated research and analysis program, we have an applications program, and we have a technology development program. Of those 4 elements, the 3 non-flight ones, that is RNA, technology development, and applications, correspond to about 40% of our annual budget. The flight mission, so I call that the science or the non-flight part. The flight mission part, which includes the production of standard products and sort of mindlessly driving around satellites and things, corresponds to 60%. It is really important to us to be a science agency with a viable science program that has access to space, as well as a space agency that does science. We don't have to beg people to analyze our data. We support people to analyze the data. And we found that in the Earth arena, at least, that's the only way that we can apply multiple satellite data sets in an integrated way to individual science problems, as opposed to generating science problems for an individual flight mission.
So you put that a very clear case for the way NASA does things. I think that requires some sort of ESA response. Shall we say?
Oh, that's very difficult. I fully understand, and I agree with Michael, and also with you, the fact that we probably putting more funds on developing satellites and probably also on future missions, and probably a bit less on the data exploitation. But this, I don't have the numbers, but I can say that we are putting more and more attention on this, and as I said before, we are trying to also to get resources in order to increase, I will say, the budget for making sure that our data is available. Our data is in the hands of the science, on the side and science people. Indeed, the budgets are completely different, as you know, but definitely I agree with you. Is a roadmap for better use.
So, are there signs that you know, the balance may change in the future?
I think we have to wait for the Council of 2016. We have a clear idea of what we have to present. And of course, there are figures which we're now discussing. I guess that there might be some changes, and there might be some new figures and new percentages to put in these blocks.
Just to augment a little bit what Mike said, there are other federal agencies in the U.S. that do provide the science support, the National Science Foundation, perhaps not so much in the earth science area, but certainly, and Art can speak better to this in the heliophysics, but in the astronomy area as well. Their budget is much smaller than anything that NASA has. Nevertheless, it is really focused on the research and analysis type of activities and developing large models.
Yeah, I was going to say something similar for the science mission, because in the science program, essentially, missions are a sort of collaboration between ESA and the funding agencies, the national funding agencies. Usually, for example, the payload elements come not from the ESA budget, but come from the budget of the member states with support to the PIs. So in this area, the PIs have also a program for the scientific exploitation. And therefore, is not part of the science costs, essentially, this scientific exploitation of the data, because it's a difficult balance in which ESA has to play, of course, the role of the preservation of the data, the provision of tools to make the best effort to achieve the scientific objectives of the use of the data. But at the same time, there are national institutions, there are institutes in which the scientific groups work and want to continue to work in order to exploit, at best, the scientific return from the science missions.
Maybe if I may add the heliophysics perspective, our research budget has been, by percentage, rather low. But we have in the US a very useful system going to the National Academy of Sciences, which issued in 2013 the heliophysics-related decadal survey to map out the next 10 years of heliophysics. And there was a strong endorsement of the research program and a strong request for increasing it. And it had the effect that the current president's budget for the out years shows a significant increase in heliophysics RNA that will really help out with the large number of proposals with good science in them that we currently cannot fund.
Well, look, okay, I think that was a really useful discussion. I think we have some more questions, so we'll wrap on that. But I think my take-home message is that we in Europe have a little bit of catch-up to do, maybe. So I think it was actually, yeah, okay.
Right. Glenn Orton, Jet Propulsion Laboratory. I did want to take a comment, if you'll entertain one, rather than a question, segueing from this discussion on behalf of the Juno science team. As was the case with Rosetta, but even to a greater substantial extent, the Juno mission has been extending an invitation to add and coordinate Earth-based observations, both Earth proximal and ground-based things, which will help the mission into a major coordinated extent. The current version of that has a massive level of international cooperation with facilities from around the world, which include both Japanese satellites, ESO, as opposed to ESA assets, and NASA. NASA has a program, in fact, to provide essential support from that. I wasn't sure to what extent that might exist on the European side. For example, people consider the Juno mission as beginning in July and moving onward, but in fact right now we're less than 1 AU from Jupiter and impinging closer and closer to the planet and measuring the very characteristics of the particle in the field in the solar wind that are impinging on the planet, and at the same time measuring the auroral response and measuring the outbursts of IO, if there are any, and many other aspects of the planet. With data exchanges possible between the individuals who are making the Earth.
Yeah, I think so. You're talking about phase A or pre-phase A studies, things like that. I mean, ESA do, of course, they support that kind of research. What I was actually talking about was once you've launched, once the mission is in orbit, you know, what happens then? But yeah, I think
understood. When the mission is working, and
thanks for
pre-phase A, then the fact that the whole and making people aware that this whole community, I'm not speaking to the people on stage as much as the people behind and around me here, that those opportunities still exist, and there is a point person, namely me, on the Juno mission that does that kind of coordination, and we should encourage that sort of thing with support for ground-based and Earth proximal assets.
Okay, thanks for the comment.
May I just give a comment on this comment?
Okay.
Because let me recall that now we have in place between ESA and ESO a global framework agreement that goes exactly in the direction of trying to, first of all, find commonalities in terms of objectives, but at the same time to put together, so to say, the resources in terms of capabilities that are on the two sides. And nowadays in the science mission, there are certainly in the plans missions that will require for the success of the scientific objectives contribution from ground-based observations. So instead of leaving this to the initiative of the single scientists in the community, we think that having in place this framework agreement will allow to build together the best possible compromise and possible collaboration in order to achieve the objectives of the mission. So it's not at the level of pre-phase A, it's at the level of exploitation of the data of the missions to achieve the success.
Okay.
Since the question has been asked about the balance between data analysis and the flight missions, the question was also brought up, or the issue of technology development was brought up as well. I'll ask about technology infusion. So it's wonderful to develop the technology, but is the appropriate balance paid to actually seeing that technology that's developed is used on future missions or near-term missions? My experience is mostly from the NASA Explorer program perspective, which has the perception of being very reluctant to take on new technology, perhaps justifiably so. But I'm wondering about the other NASA programs as well as the ESA perspective.
So I'll take a crack again from the Earth Science Division at NASA point of view. We actually use a somewhat different metric for determining whether our technology program is doing its job right. Most people look and see how many of the technology development activities make it into flight programs. And I don't think that that's actually the right way to do it. What we ask is, in our flight programs, how much was enabled by a technology development that we had initiated before. And so the basic answer there, not how much, but for each mission, was there a part that was enabled by technology development? And we hover close to 100% on that, virtually every mission. Now there is a balance, of course, between, as you pointed out, between risk and scientific risk and technology demonstration in a flight program environment. One way that one can get around that or can advance that is through focused technology in-space demonstration programs, which we are doing and which are possible in a small sat, CubeSat arena. Another way is for long-term measurements, which is perhaps unique to Earth, where we have to take long time series to actually build in a technology infusion route so that we are investing in technology early enough that it can be evaluated when we're making architecture decisions for the future, not simply recurrent spacecraft. In our Sustainable Land Imaging program, we have built that in, so on the order of 5% of that program is a technology development line, year in and year out. So that's what we're doing in Earth.
Just on the same line, let's think of Sentinels, the Sentinel missions, which are the recurrent Earth observation missions. If you think of the instruments which are flying on these satellites, they come from, all of them, it's, I would say, an upgrade of instruments which flew on our satellites with ARS-1, ARS-2, and MBSAT. So even there, we can say 100% of that technology has been enabled, has worked, and now is now flying on missions which will be there until at least another 15 or 20 years. If I think of, in my case, because I'm a little biased with Cryosat, we flew, well, the concept of a SAR radar altimeter was developed 80s, 90s. We were the first mission on Earth to fly a radar in SAR, beamforming. Well, this paved the way to a lot of new technologies and improving, which are now flying on Sentinel-3 and will be on Sentinel-6, the JAXA. So even I will say, also from the ESA perspective, that kind of enabling new technology has been successful.
May I add something on the, let's say, on this part for the science program, because it's a very important area, the technology development, of course, also for science missions. But let me recall that the beauty of our science missions is that every mission is different from the others. So if we are talking about enabling technologies at system level, this kind of investment on a medium long-term perspective is certainly needed, and there are activities in ESA to do that. By the way, it must be done again in cooperation with our member states, because at the end of the day, the knowledge and the know-how will have to be developed in the industries that at the end of the day will be involved in the mission. So it's a very dynamic process in which we interact with the member states to understand what are the lines for future technologies. But when you talk about the specific technologies for a mission going to a comet or going to Jupiter or going to the sun, there is a problem in which you have to develop in a limited number of years, possibly, the specific technologies that are required to have a success in that mission. And this, in my opinion, is the most critical part, because, again, you cannot foresee a general technology specific for a specific mission.
If I can add a bit to that, it is death to do technology development in the context of a flight mission. Ask the JWST people, James Webb Space Telescope. The key is to have a strong technology development program that covers a large dynamic range, which matures the technologies up to reasonable TRL levels so that a decision can be made to include them without heroic development, further development activities in the next flight mission. And that's why it's so important to have an enduring, broad-based, not necessarily mission-focused technology development activity in each one of the divisions or each one of the disciplines.
Oops. Let me just say something very quickly on that. With the advent of CubeSat and small sats, that I think is going to open up the possibility of developing some technologies for those technologies that are appropriate for such a small platform. It's not going to cover everything, but that's going to give us quick turnaround time without a lot of huge investment. And then most of these programs also have low Earth orbit or sounding rockets or balloon payloads or unmanned aerial vehicles in which you can work on some technologies on rather quick turnaround time. And I know you know all of this stuff, but getting it infused into the big missions is really the TRL, Valley of Death, as we all call it.
Okay, thanks for that, guys. I think we've got maybe one last question, if that's okay.
Yes, thank you. I could comment on the CubeSat also from the ESA and CNES part, where we are far behind in the way of using these technologies. But my question is more on the science collaboration, the collaboration between agencies. And we have seen that there are mission of opportunities now as a line in the ESA program. And as was said by Eric Rosner, the heliosphere program will be increasing, and there will be a mission of opportunity call as well as a SMAP for heliophysics. And we'll intend indeed to address this call in the coming months. So what is the procedure at ESA? Because up to now, it has always been very fuzzy. How do we indeed start this mission of opportunity to really get concrete?
Well, let me first, if I may, correct you about the fact that it's a new element in the program. It's there since many, many years. You know,
yes, yes.
We have had in the past with the Japanese, for example, collaboration based on this mission opportunity approach. The scheme is that the missions of opportunities require two elements. First of all, a willing partner that wants to involve ESA in participating in a mission at a moderate, low level of resources. Second, there must be a clear case for a community in Europe of scientists, in that case, to be involved and recognized by the partner in order to receive a return in terms of science. And this must be supported by the member states, because at the end of the day, we don't have for the mission opportunities call, because otherwise there will not be opportunities. In this term is the reason why it works like this. So whenever there is a mission in which Europe, ESA, is called to be a partner at that level of resources, and there is a request from the community and from the member states to discuss this at the level of the decision body, that is the Science Program Committee, this can be considered for eventual approval by the SPC.
Yes, if I can comment on this. The problem is not for the big mission, indeed, where there are disagreements between agencies that are easier. The problem is for the smaller mission, like the mission of opportunity, because we indeed have, therefore, in Europe, both the funding agency or national funding agency and the ESA, when we are several, and we will be several European countries involved, with also some space weather aspects in the proposal. So therefore, it would be better for us to have the label as a mission of opportunity ESA rather than national agency. But for that, we need ESA to closely interact with our national agencies that are not always very keen of doing small missions, like what we have seen for the ESA-CAS or KERPS before, for the first and second small missions. So if it's really a change of attitude of ESA, it should also be implemented to the national agency as a way of collaboration with them. So there is some work, I believe, on the ESA and national agencies in Europe side to make that winning process.
Yeah. It's a very complex framework, of course, what you present. Let me say that the major point for ESA Science is to participate with the program to initiatives that are not affordable at national level. That's the driving line in our approach for the contribution to the different segments that you have in the program. So whatever is done at the national level with direct collaborations with the international partners, of course, we cannot intervene or interfere. It's the other way around. If the member states consider that the involvement and the community consider that the involvement of ESA as a benefit in terms of the management of the return and the management of the interfaces, that's the case in which, if the resources involved are at the level of a mission opportunity, we expect the possibility to consider this option. We cannot interfere with the internal processes that drive the decisions of the funding agencies in their authority.
Okay, thanks very much for that. So I think we'll wrap up the discussion there, and we've just sat through about 3 hours of what you could say is rocket science. It doesn't get much more inspirational than that. I mean, it was everything from state-of-the-art Earth observation to the origin of the universe. And we gave our panelists, our speakers, a good workover, I think. So I think they really do deserve a final round of applause.
So